Right, we're just waiting for the live stream to go on YouTube. Start in half a minute. Okay, great. So I think we can start. People are slowly trickling in. Welcome again to the IUCA Thursday Colloquium. We've been doing it online for 2 years, and even though the speaker today is actually stationed in Pune, we decided to carry on this online mode. In the future, we might have a mixed version, but we haven't yet gone there yet. So I'm very happy today that our speaker is Sushmita Gupta, who has, as you know, a few months ago joined IISER Pune, which I'm happy to note is building a very substantial cosmology and astrophysics group. Sushmita did her PhD from Calcutta, St. Xavier's, then moved on to IIT Bombay and PhD in University of Illinois, Urbana-Champaign. It's been postdoc at the Kavli Institute in Stanford and then Chicago, and joined IISER Pune just earlier this year. And we're very excited. Today is a special day for black holes, as you know, and we're also very excited that compact objects and gravitational wave sources come into her new talk today. Lovely, colorful first slide. Over to you, Sushmita. We'll ask people to ask questions in person by raising the hand up later on at the end of your talk, but the floor is yours.
Yeah, thank you very much for inviting me. I'm really excited to be back in India and also with the opportunity to talk at IUCA. So I'm really hoping for extended connections over many years to come. So today I'll be talking about some very recent work that I've been doing, and this is also sort of a new area that I'm delving into in trying to sort of understand the connection between binary compact objects, which form the sources of gravitational waves, and structure formation in general. So that is what I'm going to talk about. And of course, this colorful new slide is, Starry Night by Vincent van Gogh's Starry Night. It was used for showing B-mode polarizations earlier, but I thought it's actually more apt for looking at these merging compact object binaries. All right. So to start right at the beginning, of course, this is a very exciting time for astrophysics and for cosmology. One of gravitational wave detectors have really opened up a new window into the universe. We now have a very novel way of observing and getting signals from messengers all throughout the cosmic history of the Earth. And given that now we can essentially look at the merging, measure the very distortion of space-time using ground-based interferometers is, of course, a great achievement of mankind, I feel, and also puts it at the threshold of these really exciting science that is going to come. And of course, we in India are also participating in this effort. And that will really help us bring together all of this science in the next few years. What I'll be talking about mostly is motivated by the gravitational wave signals that we've been getting from the LIGO-Virgo detectors. So these ground-based interferometer detectors are essentially measuring gravitational waves that have high frequencies that are mostly related to compact objects, which are stellar mass binaries, which are merging in the last phase of their lives, and we are measuring the gravitational wave signals from these objects. So these are mostly binary neutron stars, black hole binaries, and also neutron star black hole binaries. Of course, later we'll also be able to measure binary mergers from supermassive black holes at the centers of galaxies, also using pulsar timing arrays, and of course, the CMB measures the distortions of space-time laid down during the time of inflation. But today's talk, I will mostly be talking about the compact object stellar mass binaries that we detect in LIGO-Virgo. So in over the past few years, starting from 2015, when we first measure the merger of two black holes, we've since have sort of three observing runs of LIGO, and we have really added to the census of these exotic objects in the universe, right? So this is sort of the primary mass versus secondary mass from the first observing run. This is what we have from the second observing run, and now we're at the third observing run, and we're really populating the census of objects. So this is a figure that you have probably seen several times before. It's called Masses in the Stellar Graveyard, although I feel like these are really alive, exciting things that we are studying today. And these are basically the total population of binaries that we have measured, and both of the primary, secondary masses, and then they add up to these to the different masses. The blue points are the ones that we have measured using LIGO, and these points on the sides are essentially the EM black holes and the EM electromagnetic neutron stars and the electromagnetic black holes that we have measured using X-ray binary measurements and so on. So really, this has opened up a vast diversity of events. Even in the short span of time that this instrument has been active and we have been measuring gravitational waves, it has thrown out, a lot of surprises, essentially, from massive black holes that from the first detection that we got was from 30 solar mass massive black holes to GW170817, which was one of the most exciting events because we also saw a simultaneous electromagnetic wave counterpart to the binary neutron star merger. Then, of course, we have been finding all kinds of things. For example, we have a pair of neutron stars that are essentially the lightest known neutron star pairs. We don't see such pairs in our local galaxies. We have the largest known neutron stars or the lightest black holes that we have observed. We have also excitingly observed in GW190821, we have also possibly observed with very high significance a final black hole, which is in the intermediate mass black hole range. And also the individual components of those black holes lie in the mass cap of black holes, where we actually did not expect to see black holes of those masses. So these are all throwing in sort of all kinds of surprises. And really, like if we wanted to summarize among the different things that we've learned, I think even if we were to step back and take some of the basic lessons from the vast diversity of objects that we have discovered, of course, now we know that, independently from a completely independent proof that black holes do exist. Mergers are compact object mergers are accompanied by electromagnetic counterparts. So we saw a gravitational wave signal and a simultaneous electromagnetic signal. which an event which literally shown in like all of the frequencies, in all of the electromagnetic spectrum. Then, of course, binary black holes can merge within a Hubble time. That massive black holes exist, and also we've known that there is a potential signature for objects that live in the mass gap. So my, of course, apart from just being excited about this from the point of view of being a physicist, of course, my interest in this is also, we're really measuring the evolution. We're really looking at the evolution of stars through the history of the universe, right? Because a lot of these compact objects form out of really massive stars that tend to live for tens or 20 millions of years, right? So we won't often see the stars shine, but we're getting the gravitational wave signatures when they do end up merging from all throughout, from throughout the history of the universe. So, the most massive stars, like the POP3 stars, etc., we expect to be forming, right at the beginning of star formation in the universe. And if we do see these events, we can trace them back to really some of the earliest, most energetic events happening in the universe through the history of star formation, through the history of star formation, essentially. So in a sense, yes.
Sorry to interrupt. So I think the network is slightly unstable. So it might help if you switch off your video. So
Okay.
you'll save a little bandwidth that way.
Is it better now?
Yeah, go ahead.
Okay. Yeah, so we are essentially probing the star formation history of the entire universe, or at least the star formation history of massive stars over the entire history of the universe with these events. So for the current generation of events, we are really probing sort of like the fairly nearby universe, but the second and third generation of gravitational detectors, for example, with Einstein's telescope, we'll be probing events. Sorry. Hello? Can you hear me?
Yes, Sushmita. Go ahead.
Is the connection still unstable?
It's fine.
Okay. Yeah. From the second generation of detectors, we'll also sort of be probing much further out in redshift to the phases of the first star formation, to the epoch of reionization, etc. So, of course, a fraction of these events that we are currently probing, particularly for neutron-star mergers, that are close to us, will actually have electromagnetic counterparts. So we'll be able to probe with these electromagnetic counterparts. Oftentimes, we'll be able to associate, of course, if there is an electromagnetic counterpart. Am I unmuted?
No, you're okay.
Okay.
Go ahead, please.
So a fraction of these events will have electromagnetic counterparts, particularly for neutron-star mergers. And for a subset of these events, we'll actually be able to localize a host galaxy with it. Now, this is important because what underlying to these mergers that we're detecting, we want to answer, we want to understand these objects. We want to understand the formation, the epoch of formation, the evolution of these objects through times, and the distribution of these objects in the universe, right? And so particularly for the things that we will have electromagnetic counterparts for which we will be able to localize host galaxies, that will give us extreme power to really place them in the context of structure formation, and try to understand their different formation channels, for example, their different evolutionary properties. In particular, just given mostly compact object binaries are thought to sort of their formation channels can be sort of thought to be in two broad divisions, where they form in isolated scenarios, where they form as parts of following the stellar evolution of the universe as a subpopulation of the stars, to net number of stars that form in the galaxy, This is often known as what is called the isolated scenario. They form in pairs of binaries, or they're often thought to be formed in dynamical formation channels within dense clusters through resonant captures within globular clusters, stellar clusters, nuclear clusters, and so on. So some of the questions that we're trying to understand through the, given that we'll have going into the future statistical samples, large samples of these compact object mergers, is how these different things form and come into being. Of course, how stars end their lives and live their lives and depend a lot on how they live their lives, or the kind of environments that they lived in. This is a very sort of famous plot from Heger et al. 2022, where you're plotting the metallicity of this environment, metallicity of the star versus the initial solar mass of the star. And it shows how in different metallicity regions, you expect stars to end their lives through different processes, and therefore either end up as black holes or neutron stars. So one thing to note over here is that the most mass, like neutron stars can form over a wide range of metallicities, but the most massive black holes, if we see them through direct, and if we can attach them to direct isolated collapse, we could actually probe the lowest metallicity environments in the universe. That is essentially, the first stars that were formed. So I'll come back again to GW 170817, because that was basically one of the events that really motivated a lot of excitement, because it was seen in two of the three detectors that really helped in localizing this event. And it was the first binary neutron star merger event that was detected with an electromagnetic counterpart. It had, the final remnant had a total mass of 2.7 solar masses, and this was approximately at a redshift of 0.01, which is sort of 40 megaparsecs away from us. So it's fairly close to us, and we could see the kilonovae. We could localize it well enough and associate a kilonovae at close to the location of where we expected the most likely location of the gravitational wave merger. So this particular event was found in this galaxy called NGC 4993, which is shown here in the right. This NGC 4993, the event has been highlighted by this square region, and so we found the electromagnetic counterpart, the kilonova, to be happening somewhere offset from the center of the galaxy, in one of these caustic-like streams of this galaxy. It was the gravitational wave event. The gravitational wave signal was followed by a short GRB, sort of 1.7 seconds after we measured the signal in LIGO. So this was actually the first time we also associated a short GRB with a compact object merger and a gravitational wave signal. And what we took away, one of the things that we want to take away from this event, and will be sort of the motivation for the rest of my talk, is essentially that these binary systems evolve and grow with cosmic structure and co-evolve with the galaxies that they live in through cosmic time. And this is basically the connection that we want to really sketch out, to use the host galaxies, if we can see them, to understand the population and the evolution, and try to understand what signatures of the evolution of these systems is imprinted on the population of host galaxies that we see them in. So this is just, a simple picture that the binary lives in a galaxy. The galaxy could be a part of a cluster of galaxies, or could be in an isolated environment. And that, of course, is part of the larger cosmic structure in the universe, the vast distribution of galaxies and dark matter that has come together over billions of years. And So the subject of my talk, essentially going ahead, will be how do we understand the connection between these binaries and the galaxies that they live in? Of course, the relevant timescales, of course, what matters here are essentially the relevant timescales in the life of the progenitor stars and the life of the binary systems. In particular, we care about sort of the formation time of these systems, in the sense, when do they form? And we can then link it to when we actually see the gravitational wave merger events and when do they merge, right? And understanding this relation between the formation time and the merger times, which is often known as the merger time or the delay time, has been one of the open questions that people have tried to constrain, people have tried to answer, studying these compact object binary systems. So essentially, the idea that we're talking about here is that if these timescales between the formation of a merger event and the formation of a binary compact object system and the merger of the compact object system is of cosmological timescale, then the host galaxies themselves can evolve significantly over that time. And we have really, over decades, we have studied, even though we're only just starting to see these gravitational wave merger events, we have studied galaxy evolution, we have studied galaxy dark matter halo connections very extensively. So we can use our understanding of how galaxies evolve in the universe to extrapolate to understand how binaries evolve in the universe and how we can link them. So in this picture, what you can see is the famous Maddow-Dickinson parametrization of the cosmic star formation history. That is the buildup of all the stars in the universe and how that evolves over the entire cosmic time. So what you have here is the stellar mass density, the number of stars that form per year per megaparsec per moving volume in the universe as a function of redshift. And in particular, in the context of neutron stars, which are often thought to follow essentially the cosmic star formation, like regions of star formation, the cosmic star formation in the universe that are thought to be tied to the star formation in the universe, we expect that their distribution over time will be essentially a convolution of this cosmic star formation history and their delay time distribution. So as I was saying, we know from, we understand now from studying millions of galaxies with our vast data sets, very sophisticated data sets, and through simulations and theory, we've now understood that galaxies, if I were to draw an overall evolution, the most simplistic picture of galaxy evolution, galaxies start as being blue star forming and spiral, and with time, the star formation rate of a galaxy dies off, and the galaxy moves from being blue star forming and spiral to red, quiescent, and elliptical. So that's sort of like the life history of a star, and essentially, if the time scales relevant for binary formation are of the order of gigayears, the galaxies in which these compact objects are born and the galaxies in which they will end up merging will essentially look significantly different, depending mostly on the star formation history of a particular galaxy. So then we were asking the question that what do properties of the host galaxies actually tell us about the underlying binaries? And in particular, we were concerned with properties of galaxies like the galaxy age, so the mean population, stellar age of the population of stars in the galaxies, the color of the galaxy, which is oftentimes an indicator of the star formation rate of the galaxy, and the total net stellar mass of the galaxy, telling us, which stage of evolution the galaxy is at the time when the mergers happen. And of course, we know that different properties of galaxies tend to have different large-scale environments, different clustering properties. For example, we know that red elliptical galaxies tend to live in clusters, whereas blue star-forming galaxies tend to live much more diffusely in the Earth. So in the universe. So depending on where we find these mergers happening, we can connect them to the overall cosmic evolution of structure in the universe. So coming back to the binary formation mechanism, oftentimes these binary compact mergers are characterized by a delay time distribution. And one of the simplest forms and one of the most motivated forms of delay time distributions are essentially these power law distributions. Essentially, we expect that the merger times, the time between when the progenitor system forms and when the progenitor system merges, follows a power law with some slope alpha, which is expected to be between -1 and -1.5. And this is sort of motivated by this kind of power law behavior is expected from the distribution of the initial orbital separations of these binary systems. And there is some initial, and oftentimes it's also parameterized with some initial delay time that is associated with the merging object. So in the work that we did, we essentially tried to imprint this delay time distribution on the cosmic star formation histories of galaxies and try to understand what kind of, how these different delay time distributions, by varying the parameters of these delay time distributions of binary compact object mergers, how do they affect the final galaxy properties that they tend to live in. So the idea is essentially very simple. So even before we go into galaxies, if we just look at the net budget of stars forming in the universe, on the left here is basically the star formation, the cosmic star formation rate and the star formation history of the universe in units of age of the universe. So this is today, and this is so this is age of the universe. So this we're essentially 13 giga years old. So this is today, and this is early universe. And so that's the star formation history. And overlaid, if we think that the binary evolution essentially follows the star formation rate of the universe, we basically have the distribution of merger times that we will see at any time is essentially a convolution of the net number of stars formed over the history of the universe with the delay time distribution, which is characterized by a simple minimum delay time and a power law. So at any time, suppose we wanted to measure what is the distribution of merger times of all binaries merging within a co-moving volume at a given redshift, for example, say, so this is at redshift of 0.05, say. So we could simply basically evaluate the convolution of the delay time distribution and the star formation history, and we would get the distribution of merger times of all possible mergers taking place in the co-moving volume at that given time in the universe, which is shown here in the right panel. So of course, and then you can go out to different redshifts and you can measure the same quantity, or if you could measure the same quantity, and you would basically end up with different distributions of merger times at different epochs in the universe. And if you vary the slope, so basically you have a minimum delay time and you have some kind of slope of the distribution. So long delay times are long merger times are weighted less than high merger times. So if you have a shallower distribution of merger times, you would end up with systems which have you would end up with more systems that have long merger times than systems that have really short merger times, or systems which basically are born and merged immediately. But what is important is while this is sort of the merger time distribution of all compact binary events in the universe, at a given epoch. We can compact binary events like don't come with a tag saying that, okay, this was the merge attack, right? So what we can do at best is basically look at the distribution of these. What we can do at best is isolate these merger events and link them to galaxies. If you're lucky, we will find a host galaxy. And just by the nature of the timescales involved, imprinted on the galaxies that we see, different regions of these distributions will be mapped on to different types of galaxies. For example, if you have things with very long merger times, so this red distribution is what we see at a very low redshift, so distribution of merger times of binaries at Z of 0.05. And at Z of 0.05, things which will have long delay times, long merger times, will preferentially be in galaxies that look red and dead, because these galaxies particularly these galaxies today, have formed most of their stars at an earlier time and are older and have an older stellar population. So you're likely to have things that are formed early and have spent a long time between their formation and their delay. Whereas if you found these these mergers preferentially in blue galaxies, or rather the lower part of the merger time distribution is probed more by star forming galaxies where a lot of current star formation is happening, and on short time scales, stars are being born, they're dying, and they're merging to form these gravitational waves or electromagnetic signals. So that's sort of the basic idea, but we wanted to sort of imprint this on a larger cosmological volume, so that we can really study the distribution of these objects in the universe. So what we did is we essentially took this is work that I've done in collaboration with Maya Fischbach, Daniel Holz, and Lisa Wexler. And what we essentially did is took these delay time models and populated a dark matter only simulation with a semi-analytic galaxy formation model with these delay time distributions, and basically studied the properties of the hosts of these galaxies. So that's sort of the short version of it. So sorry. Yeah. So what we did is we took the universe machine simulations. So this is basically a semi-analytic galaxy formation, galaxy modeling simulation, which essentially is a cold dark matter simulation. It's a simulation of a cosmological volume of 250 megaparsec, which was run with n-body dark matter, cold dark matter. And we have the entire merger histories of all the halos, all the dark matter halos that form in the simulation. And the merger histories of these dark matter halos are essentially the growth histories of these merger dark matter halos are linked, we think, to the growth history of star formation of galaxies. So this is basically a simulation that tries to constrain the galaxy halo connections. And these cold dark matter simulations are essentially populated with galaxies using a simple relationship between the star formation rate of galaxies and the accretion rate or the growth rate of dark matter halos in the simulation. So it's a large project. It's a 43 parameter model. It took a long time to run. It was run by Peter Beheruzzi when he was at Stanford, working with Risa, and it's a project which took several years actually. So he took the Bolshoi simulations and populated it with galaxies with a galaxy halo model, which has about 43 parameters, and he uses all kinds of observations from the stellar mass function of galaxies to the cosmic star formation rate to the autocorrelation of that is a distribution of different types of galaxies in the universe. And he constrains his model using all these observations. And what we did is we took the best fit model from the universe machine simulations and populated them and used this cosmological volume of galaxies to populate it with neutron stars. So what do the universe machine simulations give us? Every halo that lives in the simulation has a galaxy within them. The galaxy also has, so you get a natural connection between the galaxy that lives within a cosmic structure called the dark matter halo, and you also get its entire star formation history. So we get the full star formation history of the galaxy, and we populate these simulations with the merger time model. In a sense, what we do is we take every galaxy, we say that the binary evolution is tied to the star formation rate. We populate it with a certain number of binaries and just evolve their distribution through time. And then basically ask simple questions of how once, so what we are left with is at every redshift, we have a galaxy with different properties, and also we have a galaxy with a merger rate of binaries in that galaxy from the imprint of the delay time model. So for this work, we mostly concentrated on low redshift, on the low redshift universe, mostly focusing on where we expect LIGO to detect electromagnetic counterparts. And just to summarize so far, cutting the long story short, for every galaxy in these simulations, we have a star formation history given by psi here, and we have some delay time model based on some parameters that we choose, and we populate this delay time model to evaluate a merger rate for every galaxy in the simulation. And then we essentially pick populations of galaxies weighted by their merger rates to pick most likely hosts of gravitational wave mergers or compact binary merger events, and study their properties as a function of the parameters of the delay time model. Right, so just a simple picture to keep in mind, just from the point of view of galaxy evolution. So this is just a star formation rate as a function of redshift. And these are galaxies of different stellar masses. As you can see, that galaxies, high stellar mass galaxies that have a lot of stars, tend to have a lot of stars today, 10 to 11 solar masses of stellar mass within them, tend to have formed their stars sort of much earlier. So this is today, and this is early redshift. So the majority of population of the stars in these galaxies have formed around redshift 2, whereas the lower mass galaxies have star formation rates that are, so this is just the net star formation rate. What you actually see is actually the specific star formation rate, but in any case, lower mass galaxies are still forming most of their stars today. They have not yet reached the peak of their star formation history, whereas star formation rates, whereas massive stellar mass galaxies have formed their stars earlier, close to redshift 2. So essentially, then we looked at the properties of these different galaxies. So essentially, what I'm trying to say is that once you, if the star formation rate of a galaxy is tied to the binary formation, then for a high mass galaxy, most of its binary systems would have formed also closer to the peak of star formation. And the ones that are merging today, that we see merging today, would be ones that have more likely have had longer delay times between their formations and their mergers. So we studied, so we varied our parameter models and studied various properties of the host galaxies of these events. And this is simply the instantaneous star formation rate versus stellar mass distribution plane of galaxies that have very short, of mergers that have very short merger times, of compact object mergers, binaries that have very short merger times. So this is like a very short minimum delay time model. And in usual, generally the contour of this plot is the usual specific star formation rate stellar mass contour, where you have this star forming wing and this low star forming cloud. And if you have really low delay times, very short delay times, you would most of your mergers, if the underlying model of mergers have very low delay times, most of your mergers would be happening in galaxies lying in this star forming wing. And if you had really high delay times, you would have most of your mergers happening in high stellar mass galaxies with low star formation rates. This one data point over here is the one electromagnetic counterpart host galaxy that we have from LIGO, which is GW170817, and that's kind of sort of like a little bit of an outlier galaxy, but it has large enough error bars, and it's also one event really. But it's been known for a while that the galaxy has somewhat of a low star formation rate for its mass. And so this is just a figure showing essentially how your host galaxies would move in this plane of specific star formation rate and stellar mass as and when you change your underlying delay time parameters in the model. And we can use this. We can use these simulations to sort of use the distribution of galaxies to constrain if you were to ever measure a population of galaxies with hosts around them. So we also looked at different properties like their host dark matter halos and their local environments. For example, this here as a function of the delay time, underlying delay time models of the binaries. As one would expect, this is the halo velocity, dark matter halo. So this is the host halo within which your galaxy lives, within which your galaxy is a central galaxy. And the velocity dispersion is essentially a tracer of its mass. So as expected, longer delay time mergers would more likely be biased towards living in massive halos, whereas short delay times would be more biased in living in low mass halos that are probably closer to these Milky Way-like systems actually. And that of course also has a significant effect on the bias of these systems. This is something that we understand from cosmic structure formation, that massive halos tend to live in regions of the universe that have very dense dark matter distribution, whereas this is just simply the mass bias of halos. So the overall biasing of these events would be a function of the underlying delay time distributions of these merger events. So then we did some simple exercises asking how many events, how many host galaxies, not events, would we need to actually start putting reasonable constraints on these delay time parameters, like the slope and the minimum delay time. And optimistically, with 30 events, we would start to sort of rule out different parts of the parameter space. And of course, if we ever were to have 100 host galaxies, we would really start narrowing down our contours. But of course, just to keep in mind, so far we've had only one electromagnetic counterpart. So going ahead, it'll be interesting to see how well we can actually constrain these. So we also asked some very simple questions about the distribution of host galaxies. If we, simply, oftentimes, particularly for localization, for these sort of, dark siren events, etc., we try to do a blind host association. oftentimes these are done based on the galaxy's stellar mass. So we asked, what would the distributions look like if you forget about the delay time just models, but if you simply ask the questions of, okay, if these mergers simply follow the stellar mass of a galaxy, the halo mass of the galaxy, the star formation rate of the galaxy, and so on, or are they drawn from a random sample of galaxies? And if that were the case, if we were just drawing from a random sample of galaxies, we would of course see a distribution of stellar masses of the host galaxies shown by this gray region, which would be peaked towards lower masses, because that's just how the galaxy stellar mass function looks. It would turn over at some low mass. Whereas if we were looking at things that were tracing the stellar mass of galaxies, if binaries were tracing the stellar mass of the galaxies, we would see the green curve. If they were tracing the halo mass, we would see the blue curve. And if they were just tracing star formation rate, we would see the blue curve in the stellar mass distribution. Similarly, we would also have separate distributions of star formation rate distributions of the host galaxies, depending on which properties of galaxies these events trace. And then just simply looking at these distributions, we would actually require very few events to sort of rule out one or the other, right? So we saw that even with of the order of so log R here is the Bayesian ratio. So even of the order of few tens of events, we can already sort of start to distinguish between a star formation rate weighted sample from a halo mass weighted sample, and these different combinations, and also just we would be able to rule out whether or not they're being drawn from a random selection of galaxies based on only a few tens of events. So I think we found that we need order hundreds of events to distinguish between mixture models. I'm not sure yet, so I'm not getting going to. Okay, so just in case you're wondering why a system would follow, for example, halo mass, why mergers would follow halo mass, particularly for black holes, this might be interesting because they're oftentimes thought to be forming through dynamical channels within globular clusters. For example, they tend to follow the halo mass rather than actually the galaxy stellar mass. So we would start to kind of distinguish between events with sort of order of tens to 100 events in the future. And then we also did some simple evaluation for the one event that we have, NGC 4993, and we found that the delay time and the plot on the right essentially is the solid curve is showing the probability the likelihood distribution of what the delay time could have been for NGC 4993. And it's one event. We have a significantly wide area, but hopefully with time we'll add more and more events to this. I will not go into this. We also found some oddities in NGC 4993 itself. So essentially, to summarize this part of the talk, the delay time distributions strongly affect the properties, the underlying delay time distributions strongly affect the properties of the host galaxies, their stellar mass distributions, their star formation rate distributions, and even the clustering of the events in the sky. For example, this is sort of the universe and gravitational waves. If we could see all the events for short delay times, we would see them much more scattered in the sky, much less clustered than if they had very long delay times. And this is simply because of the kind of galaxies that live in the kind of host halos that have evolved through cosmic structure formation, right? Like massive galaxies tend to live in high mass halos, which tend to live in very clustered, very dense regions in the universe and have high clustering. So this can, in principle, actually also affect our search strategies for host galaxies of events where we don't have a host, or if we were to assign probabilities to host galaxies for having hosted a merger event, a gravitational wave event within a given localization area. So, if we could constrain, so basically, if these events were clustered, if we could constrain the delay time distributions, if these events are more likely to be near massive host galaxies within different, so this is just the fraction of events at different radii around massive around a cluster catalog, say of 10 to the 13 or 10 to the 12.5. And as you can see that for short delay times, you expect them to be not far from massive hosts, but essentially not. Most of the events would be pretty far from the clusters, but for really long delay time, a majority of the events would be within a few megaparsec of, almost 80% of the events would be within a few megaparsec of clusters, for example. So you could look at a cluster catalog and sort of scan the area around it and assign probabilities based on different galaxy properties for them to host merger events. Right. So this was more sort of an exploration from the simulation side of what would be the properties of galaxies that host merger events, and how it would change or affect our search strategies, and how we could motivate search strategies based on host galaxy properties if we could find ways of constraining the delay time models. And have some time left. So in the last few minutes, I'll just switch gears a little bit. And actually, although I'll switch gears, it's intimately related to this. So while working on this particular paper, one of the things that almost many people pointed out is essentially, while LIGO is giving us binary neutron star mergers, gravitational waves, we have over the years many short GRBs, right? Which have not maybe been associated observationally always with compact object mergers, but over a vast amount of literature, these are also thought to be associated with binary neutron star systems. So one of the things that we are working on now is to look at short GRBs and their host galaxies, and to use the properties of their host galaxies to constrain possible delay time models of progenitor compact object systems. So this is just a figure from Wenfei Fong and Ido Burger's paper from 2013, showing basically these red circles are the localizations of the short GRBs and their associated host galaxies. And in fact, some very recent work by Wenfei Fong's student has essentially taken the population of short GRBs from Swift and X-ray from Swift and Fermi surveys, and taken deep HST imaging. And we now have a sample of around 66 host galaxies, so associated host galaxies with these GRBs, for which we have either spectroscopic redshifts or photometric redshifts. So this is very recent work, and it'll be work that is being led by Anya Nugent, will be coming out really soon. So we took those host galaxies, and actually we took the individual host galaxies, even not going into simulations, and fitted their basically light profiles with simple delayed Taut models to get some star formation history for these galaxies, and then populated the star formation histories of these galaxies with delay time distributions, and basically used them to constrain what the delay time distributions of these of the compact object systems underlying these short gamma ray bursts should be. So we have, from the GRB sample, we actually have very good constraints on the delay time distribution, the minimum delay time distribution and the slope of the delay time distribution, using just a population of 66 gamma ray bursts with host galaxies. So in particular, we want to look at this, since I've described the model so far, mostly in terms of the minimum delay time and the slope of the distribution. We're getting that the minimum delay time is around 140 million years and the slope is around -1.6. And these are the contours. The different lines just correspond to different subsamples, which have spectroscopy versus which have photometry, etc. So this actually gives us an independent handle on trying to constrain the delay time distributions of possible compact object binary systems using short gamma ray bursts. So the census of actually gravitational wave events that will have host galaxies will take significant amount of time to build up to of order 100. But we can already start answering these questions using short gamma ray bursts and sort of predict where the neutrons, for example, the neutron star cosmic merger rate evolution should be, and therefore what should be the merger, the distribution of gravitational wave events that we will get over different redshifts using what we constrain from these short GRBs. So this plot is basically showing the merger rate of binary neutron star host constraints from short GRBs using the 66 hosts as a function of redshift. The black curve is the cosmic star formation history, and the colored curves are basically draws from the best fit parameters. The peak is shifted from the cosmic star formation history, and we find that the peak of binary neutron star mergers should be around 1.6 to 1.7. And going forward, it'll be really interesting to compare this to what we get from gravitational wave mergers. So even though we won't get electromagnetic counterparts for gravitational wave mergers, we will get a very robust redshift distribution, and that'll help us compare these to a much finer level. So we also did some sort of census of host galaxy properties. One interesting thing that we're finding is that there are a lot of these short GRBs that live in really low mass galaxies, sort of even lower stellar mass than LMC-like systems. And we're trying to populate simulations to see how it really adds up with the entire picture of cosmic star formation. So on the left panel is the star formation rate distribution of galaxies where merger should happen. The solid lines are taken from simulations populated with different merger time models. The light ones are long delay times, and the dark green lines are short delay times. The blue bands are the GRB star formation rate post distribution. The star formation rates seem consistent, but what we are finding is that the GRBs tend to live in sort of lower stellar mass galaxies than simulations would actually predict for even like really feasible models of delay time. So there's some mysteries to be solved there. I think essentially what we're trying to do is trying to bring together, sort of what we learned from these short GRB systems as preparation sort of for the gravitational wave systems, and basically trying to understand the interconnection between these systems and what we can learn about the underlying populations of these binary systems. I think with that, I'll stop, and I'll take questions, and thank you. Yeah.
Thanks very much, Sushmita. Wonderful talk. Can you can now turn on your video? I think that should be all right. Let's see if there are any questions. Please raise your Zoom hand if you have questions. Shanjit to begin with. Shanjit, go on.
Hi, Sushmita. Can you hear me?
Yes.
Okay. Very nice talk. I have actually a couple of questions, but I'll ask the one question first, and then later on come back. So the last slide you showed about the first party of talk, where where you are saying that if the mergers are found in a dense environment versus in a less dense environment, then you could already kind of distinguish between the I think that slide. So,
Yeah.
but with the present detections, even though we don't have enough binary neutron stars, but we have black holes. And people are kind of trying to estimate Hubble constant, for example, without any electromagnetic counterpart. Can you already put some kind of constraints using the 100 detections that we already have?
Yes, I actually, so people have been, say, trying to making some very initial efforts to measure clustering of these 100 binary black holes that they have found. It's quite challenging because it's 100, but yeah, I think it's really interesting because I think so far all the effort has been using sort of cross correlations, autocorrelations. You could try to cross correlate with galaxies and see that if these binary black holes sort of prefer to live in highly dense galaxy regions, for example. I think it can be done. I mean,
the thing is that with O4 the number is going to is expected to increase quite a bit. I mean, by the time we hit 1,000 mergers, that time is not too far away. Meaning it could be in few years, but it is not very clear by how much time we can actually get 100 binary neutron star merger. I mean, of course, with LIGO India and so on coming online, that things may become better because the localization can improve. But that 100 is quite far away. But 1,000 black hole mergers seems to be much more feasible.
Sorry, you got cut off.
I said
that.
Yeah,
I think that's really waiting to be done.
So maybe if something could be done with black holes, it would be really nice. I mean, you're already. I'll come back to the second question later on after others are done.
Okay, thanks, Shonjit. You can lower your hand and I'll call you again. Tithankar next.
Hi, thanks for the talk. So, see the event rates the probabilities you are calculating is a convolution of your delay time profile with the star formation rate. And I understand that you have varied the parameters of the delay time and tried to see how things look. But have you kind of worried about the uncertainties in the star formation rate, particularly at high redshifts? Can they be important for example, long delay times? And how will the results then change?
Yes, absolutely. So we, particularly for the short GRB analysis that we have done, we have sort of marginalized. So we did one version with just the cosmic star formation history. We have tried to marginalize over the error bars in the cosmic star formation history at large redshift. So that obviously matters. But of course, a lot of the information comes from where the peak happens, where we have better data. So that peak shape is imprinted in particularly the lower redshift distribution that we see. So that helps us a bit. But actually, one of the exciting things about these even binary black hole mergers and their redshift distribution, binary neutron star mergers, is that we will be able to constrain that large redshift end of the cosmic star formation history. So currently what we've done is we've included it in our error bars when making predictions for.
But to constrain the star formation history, you probably need to assume something about this T, D, and alpha, right?
Yes.
For example, how do you know they're not varying with the redshifts?
You're right. I mean, all these things need to be accounted for. Like currently with the simple model, you could try to get joint constraints and there will be some degenerate space, but there might be motivation for taking more. There is motivation maybe for taking sort of mixture model, how this evolves, how the parameters evolve with time and all of that. Yeah, for sure.
Okay, thank you. Yeah.
Great. Anybody else? Otherwise, I go back to Shonjit for his next question.
Okay. So my other question was that when you were taking this delay time distribution, if the you are varying the parameter, but suppose they are forming in a dense environment, the delay time could be significantly shorter than if they are going in some common envelope kind of evolution. But are you using a completely different model, or it is the same kind of parameterization with for halos and other parts of the galaxy? It's kind of the same.
Yeah. So this is actually this. Yeah. So this is for the isolated scenario. So it's not for the dense cluster, like dense stellar cluster evolution, because there you're right that the time scales could be much faster in these dense star cluster environments. So this is mostly for the isolated scenario, and it's for, I think neutron stars are expected to more likely be in the in this isolated channel rather than the dynamical evolution channel, whereas for black holes, a significant portion of those could actually be forming in these dense stellar cluster systems. So this work is more focused on that isolated channel. Yeah.
So that is true that, like, probably the neutron stars are going to evaporate from the but I don't know what happens in the very early universe, like because initially the number of these stars are maybe there, right, at high redshift. I don't know exactly. Before they evaporate, there maybe some neutron stars would be there in the globular clusters, and like with the three body interactions, they may actually merge, and then you can get something in the early universe part.
Yeah, that's.
So
I mean, unless from these systems. Yeah, I mean, I don't know what fraction of neutron stars will end up in those systems, but yeah, it's something.
I mean, since you are also considering black hole neutron star ones, NSBH one, of course, it is not clear whether we will be able to do electromagnetic follow-up if NSBH happen in our very early universe, because it is going to be faint and far away.
Yeah.
But if they are at some point visible, maybe let's say we can do electromagnetic follow-up with 30-meter telescope or something. It is not impossible, right? I mean, it is possible that with next generation 40-kilometer detectors, when you detect something and then follow up with, then maybe we can reach very high redshift, and then these things can become possible.
Yeah. No, I agree. I mean, even without host galaxy, sort of like just the redshift distribution of events also has a lot of signatures of these different kinds of formation scenario. Like, for example, globular cluster, the peak of globular cluster formation is sort of shifted to an earlier time compared to the peak of star formation. So, you could try to sort of look for those kind of signatures as well in the distribution of events and so on. Yeah, but overall, I think it's like wide open and lots of interesting questions to explore in this field. Yeah.
Okay, thanks.
Thank you, Sushmita. If there are no more questions, I mean, let me also thank you for this wonderful talk, and hope to see you in IUCAA very soon. Zoom applause.
Thank you so much.
Thank you, everybody, and thanks everybody for coming.
Thank you. Nice. I hope to meet you all in person soon. So yeah.
Bye-bye.
All right. Bye, Sushmita.
Bye.